Welcome, and thank you for tuning in. You're listening to the Beyond 50 radio program. I'm Daniel Davis. On the program today, we're going to take a fun exploration into the world of science and space, especially when it comes to trying to understand some of the many things that we're being, showcased when it comes to movies. You know, movies such as these superhero movies that we watch, and currently the newest Star Wars. A lot of times we're being told, or at least shared with things that we kind of try to understand, what is it exactly they're talking about when it comes to, things like time travel, quantum physics, and black matter. Joining us here on the Beyond 50 radio program today is our guest who actually received his Ph.D. and also founded his first company which focused on airplane oceanography, remote sensing, and flying into hurricanes. He also invented several other sensor products which were used for research and anti-submarine warfare. And years later, after he served as a science advisor to former U.S. President Gerald R. Ford, he went to Japan and served as senior technical advisor for the largest Japanese engineering and construction company at the time. Returning from Japan, he also founded a company to provide witness expert forensic consulting. So he's joining us here on the program today as his newest endeavors happen to be writing science fiction. And his newest book, which I think people will find very entertaining, is a novel called 30th Century, Escape. It's a story that explores time travel by a secret society headed by a female captain, to implant a virus that would disrupt the genetic tendency towards sociopathy among a genetically altered group of humans known as syndos. I'd like to welcome to the Beyond 50 radio program today our guest and author of the book 30th Century Escape, our guest, Mark Kingston Levin. Mark, thank you for joining us here on the Beyond 50 radio program.
Well, thank you for having me.
You bet.
I'm looking forward to it.
You've got quite a background, and one of the things I didn't mention, but I'd like to now, is that in 1964, after receiving your Bachelor's of Science in Chemistry, that you actually worked on the Apollo as well as the Mars projects. Tell us about that.
Well, the Apollo program was, I was working for Boeing, and Boeing had a contract with NASA at Huntsville, Alabama, where we were there really to coordinate all the systems. Boeing is a very good systems engineering company, and NASA was having some problems putting all of these specifications, all of these various things together in a huge project. So Boeing was taking kind of the overview, and let's look at all the different systems and do some systems engineering on it. So that's kind of where I came in and was involved. I mean, we looked at things like radiation effects of materials because there's a lot more radiation in space, etc. But many other things, particularly combustion engineering. Werner von Braun was really his technology on the F1 engines. Those are the biggest engines ever built on the Saturn V, and those are basically scaled up versions to some extent, maybe a little better mixing than what he had done previously with the Atlas. And so that's really what, in a nutshell, what we did with Apollo. Now, the Mars program, von Braun was a very ambitious person. He wanted to get to Mars by 1985. This was like 1967, 1968. I can't remember exactly. But we had meetings with him to try to look at what are the long poles in the tent. What do we really got to get started on now to meet 1985? And one of the things that came up was the systems engineer called for a nuclear propulsion system in a nuclear reactor in space to be able to power the people going and coming, plus the propulsion system. Once the nuclear rocket, which was going to use hydrogen, liquid hydrogen, propelled you out towards Mars, break Earth orbit out towards Mars. Then we had ion propulsion, which would be used halfway. Then when you get halfway, you turn the ship around and you start braking with the ion propulsion system. So that's, and there were some really neat things that von Braun was kind of a student of American history and ancient history, and he decided that he was going to name the three ships, the Nina, the Pinta, and the Santa Maria. He was going to send three ships there in case you needed some redundancy. At least one ship would make it. It was capable of taking all the crew. So that was the Mars program back in the day. The nuclear rocket was actually tested at Jackass Flats. It was fired upside down onto a scale so they could measure the power, and it came in just where we thought it would. And so it was a technical success, but a funding failure because Congress quickly dropped the Mars program.
You know, you talk about all this, and it's really fascinating, especially in a day and age where when it comes to entertainment, people seem to be craving movies, especially as I was saying earlier about Star Wars, for instance. But, you know, it's one thing to watch these things happen, but it's another thing to get a grasp of the reality of how they draw their ideas. For instance, let's say what's the other one that I'm trying to think of, the Justice League. You know, when they're talking about things such as the use of dark matter. And, you know, just to give, you know, our listeners again the idea that you also studied, along with Nobel laureate Paul Dirac, in the world of quantum mechanics, and you also received your PhD in 2.5 years. So basically what I'm trying to say to the listeners here is, guys, you know, it's one thing to have all these opinions on YouTube about what you think you know, maybe studying from things, you know, such as Wikipedia. We're talking with somebody here who's wicked smart.
Well, thank you, but it is a different language. So the people of math, you know, who learn the language of mathematics,
right,
can do it. It's like trying to study in Japanese when you only speak English. You have to first learn the language, and then you can get along in Japan.
So now let's talk about how they showcase this a bit and the realities of what people are actually seeing in the world of, you know, in the world of science that you know.
Well, you know, way back when I was studying, there was a guy named Fritz Zwicky, Swiss, who was at JPL, by the way, but he was a Swiss person, born in Switzerland, and he was the first one to come up with the idea of dark matter back in the 30s. And there's a number of reasons why we want to create dark matter. One of the reasons is that the way galaxies rotate, if there wasn't any dark matter, other matter, the basic laws of Newtonian mechanics say that these things would run out, would flip, would fall apart, would come apart eventually, and we wouldn't have galaxies. So, and also in the early universe, how did galaxies evolve? They had to have some huge amount of mass to form around, and that again is part of Zawicki's originally dark matter. So he's the first guy who came up with the idea in the 30s, and then later on, people discovered that you know, the galaxies, the way they orbit, the way other things, and studying the primarily galaxies and other large bodies, which are galaxy clusters. Those are the largest bodies we know of in the universe. They're clusters of galaxies. Some of them maybe 100 galaxies. And the way these things all behave, there needs to be more matter there, or they wouldn't behave that way, according to the laws that we have physics. And one of the basics of physics is that if the laws of physics apply somewhere, it's going to apply everywhere. So, you know, that's basically held true. But anyway, when I was a student, we were studying this kind of dark matter issue a little bit. And, you know, since then, they haven't found it yet. But I just heard a talk by a woman scientist, Catherine Fries, and she says, maybe this year, maybe next year. They think they're really close. They now have like 20 or 30 sites around the. First of all, in order to look for evidence from these dark matter emissions and other things, they have to go down deep in mines or way under the ice, a couple miles, and build a big detector. So they have those in Canada and South Dakota and all across the globe. We now have these big detectors way underground in these mines. In some places, the mines are still operating, and these are just old tunnels that they finished with, and the detection systems are in there. And so they're looking. And there are some people who claim they found it, but others claim they haven't seen anything. So we have a dilemma. Well, we have to try to reproduce what the people think they saw. And that's where we were about. Well, technically, we're much more advanced, but we're still in the same position from a theoretical point of view. We haven't been able to identify dark matter yet and have it verified. So right now it's a theory, and it's not a bad theory. It's been around a long time. A lot of people are comfortable with it because the way when you build models of the evolution of from the Big Bang forward, it seems to make sense in the models. Models work when they put the dark matter in. So this is a little bit what we think we're going to find are called WIMPs. Those are weak interacting massive particles. In other words, you might have 1 billion of them going through you, and they won't hurt you because they don't interact with other matter. That's why we can't find them. So we're looking for some kind of decay where there might be an anti-WIMP and a WIMP collide, give off a photon. And if we can go and observe some of the densest parts of where we think the matter is, as the galaxy rotates, maybe we can see some of these gamma ray on the detectors. So people are looking. So the best we really think we're going to do is indirect detection by something, assuming that they collide. Very hard because they weakly interact. It's very hard to see them, but we can see the effects of the gravity. In fact, gravity lensing is something that we've used to infer that they do exist, and that is where there's a high mass, it bends light more. So the amount of light, the amount of bending of the light, Einstein first figured this out, and that's how they proved Einstein's theory, because a theory is supposed to predict something that you can test, okay, in order for it to be true science. And so Dirac predicted that the light would bend by gravity, and indeed it did, and it not only did it bend, but it bent exactly the amount he said it would bend. When we looked at things bending through our sunlight behind it, and as it came out. So the amount of bending of light by mass and gravity, because mass is, in Einstein's theory, the mass disturbs the fabric of space. That's what causes orbits, because there's a disturbance by the two masses, and this warping creates this free-falling orbit. So it's a little bit different than Newton's theory, but it proved to be correct. So that was a great plus. And let's see, I'll throw it back to you again, a follow-up question.
Well, yeah, and saying all this, it's also, when we take a look at what we're seeing today, it's the idea of time travel. And so how close are we to knowing, understanding, or even being able to do something like that?
Well, I think we're a long way away. Maybe 30th century is the right time, but maybe it'd be the 56th century. I don't know for sure. No one can predict the future, but it's a ways off, because first, we understand less than what we don't understand. In other words, we don't know 95% of the universe. We don't know. We don't know what dark matter is. and that's about 25% of the universe. I'm just giving rough numbers now. And then we have dark energy, which is 70% of the universe. So all the things that we know that are made up of atoms that interact with light and electromagnetic radiations of various kinds, like microwaves and radio waves and things, planets, pepper, salt, all that stuff. It's all, and black holes even. All this matter only amounts to 5% of the total universe. So we don't know 95%, so we're a ways off yet. But there's nothing in the laws of physics, relativity, quantum mechanics, that says you can't go back in time, or you can't, that nothing forbids time travel. There's some entropy laws, but those are related to an entire system and not just for, short, like we can remove entropy from water in our refrigerators, and we make ice. So we're essentially going against time's arrow by doing that. And a few billion years ago, the average temperature of the universe was probably about 1,000 degrees, say centigrade. Now we're about 4 degrees, 3 degrees now, I think we calculated. 3 degrees centigrade is our average temperature, 3 degrees above absolute zero. So I'm not talking about just 3 degrees. See, this would be called the K. We use, when we get down to close to absolute zero, we like to use K because K is zero, is absolute zero. And so that's 3 degrees K, or 3 degrees C above absolute zero. It's usually referred to as Kelvin, the Kelvin scale. But this is the average temperature of the universe because it's expanding. When it was first, the Big Bang started, it was very hot, extremely hot, thousands of degrees, many thousands, maybe millions of degrees. And then as it expanded, it cooled off. And so we're in the process of cooling. Of course, our sun is much warmer, but there are points. But if you take the whole space, all of space, the universe is a very big place. Some people think it's infinite, but we don't even know that. We don't even know if there's finite or infinite. So there's a lot we don't know. So as we make progress, and remember, Newton came up with his theory of gravity in the 1700s, and Einstein came up with his theory of gravity in 1914, around that period of time. So that's about 200 years. So from going from one theory to a new theory of gravity took 200 years. Let's hope it doesn't take 200 years for our next breakthrough. So that was the biggest, the first breakthrough in Newtonian mechanics was Einstein. Mm-hmm. And then in the 1920s, you had Dirac and Schrodinger who founded quantum mechanics, which was an amazing difference. And people are still trying to combine quantum mechanics with relativity. That was what Einstein spent the rest of his life trying to do. He wasn't able to succeed. And Schrodinger spent a lot of his life. Dirac spent some time on it. Other great scientists have spent a lot of time on it. And so far, the closest we've come is called string theory. And string theory is a beautiful theory in that it has very nice equations and it's relatively easy to solve. But it's yet to produce a prediction that we can test easily, like Einstein did, or Dirac when he developed quantum mechanics. He says there's going to be antimatter. It comes out of the equation. Mathematics doesn't lie. 2 years later, they found it. So, we're used to getting quick results when people predict things, like with Einstein, it may have, taken the next eclipse, and but still there was a plan and there was a prediction, and you could measure it, and you could measure it not only, you could measure it exactly, and we don't have this out of string theory yet. Hopefully soon, but string theory is the theory of everything. So it is trying to do an awful lot.
Mm-hmm.
We have four major forces, and this combines them all into one equation. Yeah, so that is an amazing thing to do, and we don't even know that can be done.
Mm-hmm.
So, when you get to the frontiers of science, we're a long way to understanding the physics of time travel. But people can take guesses at it, and in my book, Jennifer, starts trying to understand what her first lover, her love of her life, Sexton Ho, was the inventor of time travel in the 30th century. So there's some fiction to all this. It's just characters who interact, and they're people, and they have flaws, and they're human, and but they do great things. And in after he's assassinated, Jennifer tries to figure out a lot of she didn't understand. She actually was in charge of putting the time travel machine together, but she had to rely on her scientists. And basically, she was a manager, and she didn't understand the details. So she's trying to, when she goes back in time, she's stranded there, and so she studies. She wants to study physics and try to figure out what he was talking about. And with the hope someday maybe she'll be able to get back to her family in the future. She's stuck in the past. So that's a lot what that book is about. The theory is just not there yet. I mean, we would say that it's a hypothesis, that there's nothing in physics that prevents it, therefore it can be done. And that's kind of the reasoning. But there are people who've thought quite a bit about this, including Michio Kaku. What's his name? He, one of the famous TV stars in string theory, and Michio came up with a theory of time travel on his own, and I think he's one of the things that can be done, but we don't just know how it's going to be done. But there are probably many ways. If we think of it in terms of warping space and time, when you go to a black hole, time stops as you approach the black hole. It goes to infinity. The time it takes you to go from, say, 1 foot away from the event horizon to, say, 1 inch away from the event horizon would be infinity. So it takes a long time. Things really slow down when you get towards the event horizon. So basically a black hole, that was what Interstellar was all about, that movie, that If you go close to a black hole, time slows down for you, and your other people get old and you don't. And it has to do with the effects of gravity and on time, which is what Einstein's theory of relativity is all about. It depends. If you're close to a black hole, time goes very different from you. In Newton's theories, time didn't change. Everything was the same, no matter where you were. You could be in a black hole, wouldn't matter. Time was the same for you. But we got a big breakthrough in 1914. Well, actually, some in 1905, and we got real details in 1914 about relativity, and which is that it depends on where the observer is. Time depends on where the observer is. So it's called time dilation, and you can calculate it based on those things. They kind of overdid it, I think, in the movie. The book was pretty good, but the movie kind of went away from the story. And in some science fiction, they stay pretty close, like in The Martian. That was, I think, done real well. They did a great job. with that one. They didn't change the story, the novel, the writers. It's difficult to take science fiction way in the future and try to make it into a movie. First of all, you got 15 hours of reading into an hour and 45 minutes of film. That's a pretty amazing thing to do.
Mm-hmm.
So it's difficult, and they've done fairly well with many of these things. They get some of the points across that there's a difference in time, but the different theories like string theory, you have to have 10 or 11 dimensions, and a lot of people don't like that so well, and so there are people who are resisting string theory as maybe not the way to go. And there are other theories of string theory. One thing it can do is it can also try to combine. It's the theory of everything. But there are other theories out there, like the next most popular one is called loop quantum gravity, and it is just an attempt in 3 dimensions, just normal space, pretty much, in order to combine quantum mechanics with the classical theory of relativity. So you're going to try to make relativity now quantized, and so what they actually do is they quantize the space, so that space is made up of quantums. There's something called a limit. It's called Planck's constant. You can't be smaller than that. No space. So let's say if space was made of a foam, the little foam bubbles would be the size of the Planck's constant, which is really small. Okay, it would be like 10 to the minus 35 meters. That's pretty small. So there are a lot of activity going on, and it doesn't mean there's going to be a breakthrough right away. Remember, last time it took 200 years. So
right. I know it's interesting. I wanted to note too, when you brought up the name Schrodinger, I remember that there was an experiment that he was really well known for, along many, but one that I liked was the cat.
Oh, yeah.
Yeah, and I got a kick out of that because it's a matter of that once we focus our reality on something, we actually seem to create that reality. And it's really weird, although there was the movie, I believe it was not The Secret, but the What the Bleep Do We Know? And it was funny watching this because they actually decided that they had to do a follow-up movie to this. And I thought, well, no, one was actually enough. And you had all these pseudo, physics people that were in there watching this, and most of them were just hippies trying to look for, the way that they could sit around and just, create reality without doing anything. I'm like, well, I don't think that's the way it actually works, but okay, suit yourself. But the one about the cat kind of went to that degree. If you could briefly share that particular story there, I just because,
this is the cat that's. Is it alive or is it dead?
Yeah, right.
This is a theoretical experiment. Actually, Schrodinger did it theoretically, like Einstein. It's called the Gedanken experiment. In those days, everybody was publishing in German. And this is in the 30s, 20s and 30s. And Schrodinger, he was a very interesting character. He had kind of like 2 wives, or a wife and a mistress, because he couldn't have 2 wives in those days, but they all lived together happily. And as a result, he got kicked out of Princeton because he took both his wives with him when he went somewhere. And he ended up forming a school, the School for Advanced Theoretical Studies in Ireland. Ireland accepted him where he was. Okay, so this was pretty far out for those days, and the academic societies just weren't able to accept him. He was an anti-Nazi, so they kicked him out of Germany first, and then he got kicked out of England, then he got kicked out of Princeton, so he finally ended up in he was there for 17 years, and he is one of the greatest scientists of all time, had a brilliant mind. So Schrodinger said, a hypothetical experiment here, we have a cat, I have him in a box, I have some radioactive material in there. When the radioactivity decays, it's going to set off a poison. The problem is we don't know when the radioactivity is going to decay. We know what its half-life is, but it could be much later, it could be much earlier. So essentially, we've got a cat in a box, and we don't. Is he dead and alive at the same time? Because we don't know which state he's in. So he was kind of proposing that as trying to explain what is meant by quantum theory. Until you observe it, you don't know which state it's in.
Mm-hmm.
He's got to make that point. Well, we don't until we open the box. We don't know if the cat's dead or alive.
Right.
So yeah. So he was trying to make.
It's interesting the way you frame it, because I remember it seems to me when I read about this, it was something about a particle gun that you shoot, and there's only two slits, and if it goes through the one, it releases this capsule of gas and kills the cat. If it goes through the other, then the cat lives. So, you shoot this one particle, and it's either going to go into one or the other, and you can't see what's in this box or penetrate it. Nothing could except for that through one of these two slits. And so essentially, well, how do you know if the cat is alive or dead? Well, you have to open the box and decide.
Yeah.
And I was like, wow. For a long time, that was right up there. It's really cool when you get some of these concepts introduced to you and your mind chews on them for a while, because you start almost, as you say, once you begin thinking, is this possible, then you're really focused on it, and then all of a sudden, like you said, then it becomes a reality somehow. Maybe it could be years later. But
well, it's the way nature works, unfortunately, on a very small scale, on atomic scale. If you if you have a laser beam and you go through these two slits, you don't get one pattern or another pattern. You get two lines, right? You're going to get two lines. No, you get a diffraction pattern.
Right.
Like it's a wave that's going through. And this is what's confused all of the physicists, I would say, for years. And you can then kind of do the same with an electron. You got a photon, that's a particle. It's going through a slit that goes through this slit. And that slit, they interact somehow as a pair. And they form a diffraction pattern like it was a wave going through. So this is the thing that said that, you know what, let's just watch it. So they looked at it, and it's just that when you observe it, it's in either one state or the other once you look at it. But while it's forming this diffraction pattern, you can do it on film, and you have this beautiful diffraction pattern on film. And other than that's how quantum mechanics kind of came about, in order to explain how sometimes it behaves like a wave and sometimes it behaves like a particle. And that's why Schrodinger called it the wave equation. And his equation that he came up with describes all this, answers all these questions. It's because things are in various quantum states. And it's just like if you think of an atom, you have a hydrogen atom, maybe the simplest, you got a proton and an electron going around it. If the electron goes from an excited state back to the ground state, it will give off a photon of a certain wavelength, but only that wavelength. Okay, so if you go to the second excited state, then there'll be a different wavelength. But you have the first excited state, second excited state, third excited state, and you have different orbits around, so to speak. I mean, they used to, Niels Bohr tried to relate it to, so that people would understand it, related to our solar system. What it would mean is that Earth cannot be anywhere between these two. It has to be one certain location. And it can jump if it absorbs energy, like from a photon or from the universe, radiation, other things come in and absorb it. So ordinary matter interacts with radiation. But the thing is that unless this radiation is at certain values, it's not going to be absorbed. It just goes right through. It's invisible. So that's how we recognize different atoms. Now, that's what spectroscopy is all about. And why we heat it up and we look at the emissions and we see those lines, that every element has its own lines because it has its own orbital system. So that's a marvelous what chemists have been able to do with our quantum mechanics. And they've been able to make equipment that detects everything, almost every metal, every atom can be detected in this way. And analysis, not only can tell you what it is, but how much it is. By calibrating these instruments, they can get very accurate. And we have great tools today, even by looking at the sun and looking at its, that's the first spectroscopy, was looking at the sun. We see these different lines, and that tells us whether we have hydrogen, helium, carbon, iron, all the elements that can be made in the sun, and they all can't be made in the sun. For example, there are things like gold and platinum. There was just a collision. I think you may have heard about LIGO, which is a detector that detects gravity waves. And in 2016, there were two black holes that collided. I think it was in October, first one that we ever measured in terms of gravity waves. And the second one was a collision between two neutron stars. And those neutron stars, when they collided, they made more gold than the mass of the Earth.
Wow.
Now, wouldn't you like to have some of that?
We actually had a discussion on our program about currency and the history of currency, and I said, how do we ever put so much value on gold? You can't eat it. You really can't do much with it. But it was an interesting discussion. There's something I've wanted to know, and perhaps you can kind of shed some light on this, because it seems to me Stephen Hawking did. And, he's someone that I enjoy from time to time reading his works or seeing his talks. And so when it came to the idea of the Big Bang Theory and black holes, now this was just something I thought of when I was probably a young teenager about black holes when I first started hearing about them in the 1970s. So here you have this black hole that basically is a star that has died, I guess. And it creates this vacuum that just basically sucks everything, into it. And it's so powerful that it even brings in light. And then it eventually compacts down to a size, so it was said, to the size of maybe, like the size of a pin, a little pin,
yeah.
Sewing pin. And I'm thinking, okay, if this thing was so powerful, I was thinking to myself that,
it's gravity. The black hole collapses because there's no more fusion left. The material of the sun has already been fused pretty much. So it collapses down, and you get, if you took the human race and you took out the space between the atoms and the electrons that hold the atom that dimensions the electron, you could fit the whole human race in a sugar cube.
Okay. Because what I was thinking of, with the idea or with the black hole is that it condenses down and compresses. And I thought, well, that energy, to me, and this was just, young teenage thinking, would have to go somewhere, so why not an explosion and now it expands and there's your Big Bang recreating a whole new universe? That's the way I was thinking. But anyway.
Well, you probably have it right. And in my theory, well, not published yet, but I think you're right. I think what's going to happen, the way the universe is going to go, it's going to eventually form black holes, and it does now about one a second. And eventually, there will only be black holes. Black holes have life of trillions of years. This is almost infinity in most people's minds. Trillions of years, billions. Well, we're 14 billion since the Big Bang. But as eventually you go back, you're going to have only black holes. Black holes are going to combine with each other because gravity is going to come at least in one area where you have these clusters. You're going to get so many black holes, and they're going to start to combine. We have supermassive black holes at the center of every galaxy, and nobody knows how they got there because they formed the galaxy. So maybe they were there already from the last universe that had lots of big black holes, right? But when they get to a certain size, that black hole, in my theory, becomes a white hole. I'm not sure exactly what that size is, but it's probably about the mass of somewhere near a quarter of our universe. When it gets to that size, since you can't destroy mass, it's going to be there. And there's still some theory about this, what we call dark energy, that's going to everything's going to fall apart. Maybe even atoms will fall apart. But I'm not so sure that that's the truth. But we don't know. I mean, right. I can't say I can prove it's not the case, but I think what's really happening is that space is really something, like Einstein said it was a fabric. Well, fabrics are made of very fine hairs, right? Very thin, very thin. So it's made up of something, and in that something, we call it space, or some people call it space-time. Einstein liked to call it space-time, because once you have space, you have to have time. But maybe black holes make space-time, and that's why the universe is expanding, because now black holes are being formed at a very rapid rate, so we get an acceleration in the universe. But eventually, all the stars will be burned up, and they will slow down, and it will go to like zero, and so you won't continue to accelerate. If that's what space, if you make this hypothesis that that is what's causing the expansion in the universe, I mean, the question is, does it come out of, or can we express this in a mathematical form? That's what scientists want to know. Can you express that mathematical form? Well, yes, probably you can, but it might be very complex. So the thing is, can you make it into a simple form? That's what Einstein always looked for. Try to make something simple, like E equals mc squared, simple equation. Although his relativistic equation is not so simple. It's still much simpler than string theory. But string theory is supposed to be a theory of everything, so it's more complex than relativity. Relativity by itself is relatively simple. Quantum mechanics is a little bit more complicated, and it explains all the other forces of the universe except for gravity. So we've got some work to do to patch that up, and I don't know how to do it. I mean, if I did, maybe I'd have a Nobel Prize by now, but I don't.
It's probably around the corner. Remember, when you think the reality, automatically the reality may start shaping itself to become that. Right. The question is, in what time frame?
Yeah.
Because, when I was talking about, my little black hole theory, and it was just something, it's kind of fun when you get, these sort of concepts of view thrown at you, and there's a way that you understand it. I didn't study things like mathematics. I could barely even get through algebra, and I don't even think I could get through that, as far as that's concerned. But when things like this happen, again, like I said, that was about about 1979, I think it was. And it wasn't until about, I think, 10 years ago when I caught Stephen Hawking doing a lecture, and he was talking about black holes and the idea of the Big Bang Theory, and what he was saying sounded a lot like what I was thinking, and I'm not going to compare myself with Stephen Hawking, but the fact was, I was like, there's somebody that actually is showcasing an understanding that I had. That I thought, it just made sense to me. So
yeah, well, there's a lot of theoreticians who think that every time you have a every time you have a black hole, you have a white hole in another universe. In other words, this black hole goes into another universe, becomes a white hole. Because where does all the material go? I mean, that is, there are not just one or two, but, I would say certainly dozens of brilliant scientists who think in that way, and there's others who think they're crazy. So, you have a lot of controversy today in science. Between different groups, there's a lot of controversy.
Well, the other thing that you have, too, that's a real challenge, especially in science, which should be moving forward, is the idea of academia getting in the way and slowing it down. There's your event horizon right there.
Yeah.
The bureaucracy, I know I've done many interviews over the years where it showcases that very thing. For instance, just to give people an idea, there's a wonderful movie out there that's been out for a while called Anonymous. And so if you pick up the DVD and you watch, sort of like the extras, they talk about this long-going debate about whether or not Shakespeare was the actual person who wrote all these wonderful works and plays.
Right.
And they showed how Shakespeare couldn't actually sign his own name, where he was from, and for a person to write to the level that these plays were, you would have to be these things, and Shakespeare wasn't any of those things. But what makes it funny is, think about breaking down years of academia of people who built careers out of this guy's work. You're going to tell them they were all wrong, and that's what slows everything down, and it kind of sucks. That's one thing. We're talking about literature, but when we're talking about science and astrophysics and physics itself, that's an area where academia says, well, let's go this, but let's go one further, because it seems to elusively keep changing itself, so you've got to keep up at a pretty wickedly fast pace if you're ever going to get anywhere.
Yeah. Yes and no, but things are slow right now in string theory, and in a lot of people devoted their careers towards that. But a lot of people believed in Newton, and they couldn't believe in Einstein because he was against Newton. Newton was a god to them almost, and so they weren't willing to make the change. But eventually, they were convinced by the data, and Einstein's theory became, maybe in the 50s and 60s, became accepted after he died. Became accepted, but it was very controversial before that. But Hawking's, I think, made one very big breakthrough, and that's Hawking's radiation. In other words, first of all, they say nothing can escape from a black hole, but they're wrong, because Hawking's proved otherwise. There's something in quantum mechanics that you have virtual particles. Of course, they're made from what? Space. So space is something. So virtual particles are forming and recombining. When they recombine, they form energy. Virtual particles are a positron and an electron, and they form in space, and they form all the time, okay? Like, it's just happening. Okay, so you have some around a black hole, and if one particle gets into the black hole and the other gets out, that's Hawking's radiation of those two particles, of what's called virtual particles, which is kind of accepted in quantum mechanics today, virtual particle formation. So what he did is, using the theory of quantum mechanics and virtual particles, they're coming and going all the time, which means essentially the space has to be made of something, because you can't get something from nothing. And that, again, I don't think the Big Bang theory is perfect, but because it doesn't tell you where it came from. And in string theory, they tell you, well, maybe it's two universes colliding. Yeah, but the quantum mechanics says you have an infinite number of universes. And that's one interpretation of quantum mechanics. Doesn't mean it actually happened, but you can interpret it that way, because you have zero from minus infinity to infinity. You integrate over some region, and you get a probability of it being somewhere in that space. It's going to be one. If it's infinite space, you're going to have probability it's going to be one. So then you have an equation with the probability. If you take half of that space, well, it's going to be a half. So if you try to get even more detailed and you want to put it in a cubic centimeter, well, the probability is going to be pretty small. But that's the kind of the reality of quantum mechanics, is that it gives you probabilities because it gives you a wave equation. And the wave equation you solve, it gives you the quantum states of hydrogen or helium, the very simple atoms. You can solve exactly. However, when you get to more complex atoms, you have to make assumptions, and you cannot solve it because there's this multi-body problem that physics can't solve yet. Even quantum mechanics can't solve it. Well, it hasn't as of yet. In other words, we can't solve gold or uranium or even carbon. Yeah, we can get close to carbon, but it has an atomic number of around 12. Carbon, oxygen is 16, and the atomic number is 8. The atomic weight is 16 in oxygen, and the difference between atomic number and atomic weight is usually protons and neutrons. So protons gives you the atomic number, and protons and neutrons together give you the atomic weight. the electron is so light you don't hardly even count it, although today we do. There are things that are much lighter than electrons. Of course, when you were probably studying physics and chemistry, you probably were hearing that there was electrons and protons were the smallest things. But actually, protons are made up of 3 quarks, and a neutron's the same type of thing. So we now have the standard model. Here's all the particles. We found the last one, which was thought to be the God particle, because if you had weight, lots of weight, it was called the boson. Now, you've probably heard of that's done by experiment, and a couple of people got a Nobel Prize for that. I think one is Italian, one is English. I'm not absolutely sure. Maybe it was Belgian or French. I don't recall now. But anyway, European and UK got the Nobel Prize for predicting. They actually found it. The Higgs boson. They call it after Higgs, not the other guy. I don't know why. But anyway, he may have been the first one to predict it. He was a young fellow when he did that. And one of the things about winning the Nobel Prize is it's generally awarded to older people for things they did when they were young. And so that most people who get the Nobel Prize are older. They have to live a long time. It's a wonderful thing. I mean, we have great Nobel laureates. We have somebody pushing technology out there. And I know there was a Canadian who won it for detecting neutrinos. You know, they were formed in the sun, and they come through us, and they go through you, and you hardly notice them. Your body doesn't object to them, and they go through 2 miles of Earth, and then they have about $3 billion worth of heavy water down at the bottom. And the heavy water is a detector. You have to have an awful lot of it. And what happens is it will react with heavy water has a proton and a neutron, where regular water doesn't. Okay, regular water mostly has just 1 proton. Although there is, if you go to the ocean, there's plenty of deuterium in the ocean water. It's a small percent of the normal water, but you can extract it, and that's how we get heavy water for nuclear reactors and making these very big detectors, which now we have spread out around the world. And they're telling us a lot about the neutrinos. There are different types of neutrinos, but they're one of the standard model. I was talking about the standard model, and I think it was Art McDonald won his Nobel Prize for finding the various types of the 3 different types of mesons coming from the sun, and he was able to detect those with I don't know, $1 billion worth of heavy water. So they are these detectors they put around the Earth so that we can get confirmation of those and see how they compare. So now we're getting into what's called multiple systems to detect things, and we're doing some under the ice and different things. And so there's very serious government and international cooperation in order to find these fundamental, to solve some of the fundamental problems. But the standard model is good. It's been a great progress that I've seen, over the years from when I was in graduate school till now. It's been completed. It was kind of completed when they found the boson in 2016, and now some people say, oh, there has to be symmetry. There's got to be another table in another dimension or something like this. So it's possible. We can't disprove it. What kind of experiment could you do that would show that there are not some other dimensions? Well, we don't know. That's why you can't disprove all these other dimensions.
It's funny you should say that, too, about proving and disproving, is a lot of times as we post our interviews onto YouTube so people can actually listen to them at their convenience, we got quite a lot of number of people, many subscribers, and some of these things we've posted, have long threads of discussions, and there'll be times that I'll be in it in the beginning, but then I back off and everybody else just gets into this continuing conversation of all kinds of different things that we do. And it's funny because sometimes you get these people that'll come on there and they just act like they're experts in something, right? And so they'll go and they'll fire away at you at your limited understanding compared to their galactic understanding of a subject matter. And all I have to simply say is, what evidence do you have that what you're saying is true? And then you never hear from them again. I mean, it's just as simple as that. You'll see other people create arguments and get into these verbal fights, and it's like, but what evidence do you have that what you're saying is true? And it's something I kind of wanted to end the show on here. When you were talking about the Nobel Prize, here's a character that really years before, as I was actually beginning to study and read a lot about Eastern philosophies and things like that, is that it would be probably almost 15 years later as I started this quest, that I would run into somebody that actually echoed the same sentiments of something that I had actually read as I was reading through these philosophies, and that is the German theoretical physicist Werner Heisenberg. And what I liked about his ideals is this, that once you begin observing a phenomenon, whatever it may be, you automatically change its nature because now you're interactively involved with it. And I think that, when you take a look at science, and everybody's touting science, especially these direct marketing companies with their their nutraceuticals or whatever it is, this has got the backing of science. And you take a look and you say, but there's such bias in this. Of course you're going to try to find a way to prove that what you're showcasing is right. It's just like the news. You watch news to support the way that you see or perceive things. How do you grow and learn from something like that? So there's Heisenberg. You're going to argue with a guy like that says, no, once you're involved in the observation, then you're interactive into it. You've changed it. So how do you know that that's the way it is? Much like Schrodinger's cat. Until you open the box, you don't know whether the cat's alive or dead. It really gets your mind twisting around a lot of things.
Yeah, the Schrodinger uncertainty principle basically says that you cannot measure something and know its position, because when you measure it, if it's very small, you're going to disturb it.
Right.
You're going to change it. Yeah. Mm-hmm. So the Schrodinger uncertainty principle, he got his PhD, one page. His thesis was one page. He derived the uncertainty principle. So he was also head of the atomic or nuclear bomb program for the Germans, and he did not proceed very rapidly on that, I think intentionally. And I think he tried to pass information to Niels Bohr when he visited, but I think he got confused. And so when Niels Bohr came to the United States, he said that the Germans were working on the nuclear bomb project because he had mentioned something about it. And they were actually not, because they had determined the war would be over before they could develop it. But they did make the heavy water, by the way. That was in Norway. They had the low cost electric power in Norway, a huge electric dam up there with no people. And so they used that power to make heavy water. It takes power. And separating water from heavy water, it's a big, long process, industrial process. And, of course, that was heavy water was, when it was sent to Germany, it went across a very deep lake, and all the Norwegian children and mothers and fathers and other people were on it, and the crew. They blew it up and sank to the bottom of the of that lake, and that was a resistance, which was being run by some of the English were providing the explosives and other things to the Norwegians to do that. Anyway, it's a very famous story. I think they made a movie of it about this moment where they had to sacrifice the people because the heavy water in Nazis' hands was going to be something too horrible to think about. Because if you put uranium inside of heavy water, it starts to react, and you make plutonium. Enough. Usually do it in the form of rods. That was the theory at the time. and it worked. And there were a number of good engineers who were also physicists, nuclear physicists. One of them was named Wigner. He won a Nobel Prize for something in physics, but he also built the first nuclear reactor, was his design. And he was from Hungary, but he came because he was an anti-Nazi, so he had to get out in the 30s, and he came to the United States and built up his reputation here, and then was asked by Oppenheimer to build the nuclear reactor at what's it called? It's Richmond, right near Richmond, Washington State, in the desert there, over the other side of the mountains. There's an area, Northwest Pacific Laboratory, it's called now, but it was called something else then. But anyway, it's where we made the plutonium bomb, the plutonium from the bomb, and just heavy water and uranium, so it's a heavy water reactor, and it was didn't require any enrichment, and that was the big advantage of the heavy water. The Canadians went heavy water. We went with light water reactors. Mm-hmm. Canadians have heavy water reactors. There's not a big difference between them, but since we wanted to make uranium bombs as well as plutonium bombs, but from a physics point of view, plutonium bombs are smaller and easier. The only problem is that after about 5 years, you have natural decay, and it produces something called americium, which is fairly hot. And meaning hot, it gives off gamma rays, very high energy photons are called gamma rays. And they have to take it out, so they have to reprocess it and then put it back so it doesn't get too hot so that people can find it too easily, or it comes, for a variety of other reasons. They want to keep that background radiation down. Otherwise, you have to put it in a mine in order to keep it from being detected, or submarine. So
it'd be something definitely we'd have to, unfortunately, Mark, have for another conversation here, but it certainly was a fascinating one today. Is there a website people can find out more about your books and your work, things like that?
Yeah, it's 30th Century. It's 30th century.org.
Okay, 30thcentury.org. Remember, when you begin to read Mark's books, you automatically change their reality.
Yes.
Mark, thank you so much for joining us here on the program today. It's been a pleasure. We'll have to see about exploring, the idea of nuclear energy, things like that, to a place that maybe one day we'll probably get to that point Tesla was trying to get to, that we can all extract all the energy we'll ever need, without having to by bypassing the middleman, and who knows, maybe even time travel, so you never have to be someone who's worried about being late for work.
Yeah.
Practical application, just like Einstein was trying to do.
Yeah.
Mark, thank you for being on the program.
Well, thank you. I enjoyed it very much, and I wish you the best. Have a Merry Christmas. Happy
You too.
New Year.
You betcha.
Bye-bye.
Well, thank you to the listeners out there. If you're going to do a little time travel to beyond50radio.com. That is the number 50. Discover our weekly e-newsletter that you can get absolutely free and stay up to date with what's going on in the world of Beyond 50, as well as our upcoming programs. I'm Daniel Davis. Thank you for joining us. This is the Beyond 50 radio program, and remember, live your day past halfway.